Thanks so much. Yeah, so I have a thing for animals, and I found a reason to wear this outrageous shirt today, which has pigs and kittens on it, and I hope this is my new holiday tradition, is this shirt. So we're going with that. So it's great to be back at AoT. The last time I was here, I talked a lot about dust because that's my day job, and that's my AoT name is Dr. Dustbuster. I work on trying to understand the dustiest things in the universe. But today I'm going to talk to you about something slightly different, but I also am really excited about and have been working on more recently, and that is trying to understand how galaxy clusters form and evolve. So galaxy clusters are the most massive gravitationally bound things in the entire universe. That's it. That's, the buck stops at galaxy clusters. And in many ways, they are the universe's Austins. They're the metropolitan areas. It's where all of the action is on the largest scales. And so I'll explain a little bit about why galaxy clusters are even more like Austin than you might think. Okay, so you might ask an initial question. Okay, so what's a galaxy cluster? It's a group of galaxies, got that. But you might wonder how different it is from, quote, regular space, right? So here are some images of the Hubble Frontier Field. So this was a recent program from the Hubble Space Telescope in the past few years to take very deep images in the vicinity of these 6 galaxy clusters, and they're shown on top. And on the bottom is kind of a comparison image of blank sky next to the galaxy cluster. Hubble has this neat mode where you can basically take 2 images at once, and they're pointed in slightly different directions. And so the primary science goal of this program was to look at the galaxy cluster, and they also got this deep imaging of blank sky alongside it. So that gives you a comparison. You see much more much denser fields on the top row than on the bottom. Okay, so, but, those are beautiful pictures, but you might wonder where these galaxy clusters come from. Why are these collections of galaxies out there? And, galaxies aren't just sprinkled any old random way. And they will cluster together. So, you might have seen this image in a previous AoT talk for the regulars. This is a cosmic microwave background, and it's a snapshot of the leftover energy from the Big Bang as it was seen emitted from the entire universe 400,000 years after the Big Bang. It's really a remarkable image, and it covers the entire sky. So that oblong shape is supposed to be a projection of the entire sky. So you look in any direction, and you'll see this radiation. But there are small, so it's mostly uniform, this cosmic microwave background, but there are small deviations in the temperature, which maps to the density of the universe at this very early time in its history. And so the formation of galaxy clusters basically follows this like snowball effect. You start with a little seed, a little region of the universe that's a bit denser, and it compounds, and suddenly you have the most massive thing in the universe. So I've left this intermediate stage of everything that happens in between to grow the cluster. I've left that with a big question mark. Things happen. We'll get to that in a second. And say 5 billion years later, 10 billion years later, you have a remarkable galaxy cluster. It can contain hundreds to thousands of individual galaxies. And get this, okay, so the total mass of a galaxy cluster, it's hard to really think about the scale of these things, but it contains 10 to the 15 times the mass of the sun. Okay, so what is 10 to the 15? I don't even know. Is there an abbreviation for that? A lot. Yeah, so it's 1 million billion, just to put that in perspective. It's a lot of mass. And if you took all of the mass of the Milky Way, like absolutely everything, including the dark matter, it's roughly like 1,000 times the mass of the Milky Way. And in terms of its size, again, this is like, astronomical quantities. It's hard to have an intuition, but it's 3 to 6 million light years across. And that seems big, but it actually is pretty small considering how massive these things are. Okay, so what about this this nebulous phase before, like where things just kind of happen and then you have a galaxy cluster? So that's the area of research we're trying to pursue now. We're trying to understand how these clusters build and form. And you might know Wada Merger Jr. From previous AoT talks. She's a graduate student working with me, Jackie Champagne, and her thesis really focuses on trying to understand the process by which these form. And my little analogy here is, you might have a little snowball going down a hill quickly, just like a nice smooth hill, or it can be a bumpy hill. We don't know, what that process looks like. And it would be great if we could get observations to tell us. So just to illustrate how hard that is, if you want to do this, you look for these things called protoclusters. So protoclusters are just things that we think will become galaxy clusters. But we have to look in the distant past for them. So they're faint. It's hard to find them. And they're not as centrally concentrated as galaxy clusters. So here's an image. Can anyone spot the protocluster? Any attempts? Yeah, okay, no. So these little circles encapsulate galaxies that sit in a structure. I know it was super obvious. Yeah, so I didn't think so. So that illustrates why it's so difficult to really pin down observationally how galaxy clusters form. Okay. But now I'm going to show you a beautiful simulation. It's not mine. It belongs to the illustrious TNG simulation. That's the next generation of illustrious. And you can check out and watch all of their cool movies at that website. And these cosmological simulations are kind of the link that we take from our observations. We have the cosmic microwave background. We have galaxy clusters, not a lot in between. We use simulations to patch that story together. So the steps of the simulation are that the cosmic web forms from small perturbations in the density of the primordial soup, which is like the initial gas. Runaway gravity condenses clouds to form stars, groups of stars, and galaxies. The nodes of the cosmic web will grow most quickly and funnel material from filaments. The deep gravitational well will heat gas in those center density points, and it'll actually strip gas off of galaxies too, and have a very high concentration of very hot gas. And then clusters eventually amass hundreds to thousands of galaxies over the course of 10 billion years. So that's a very broad brush picture and a really beautiful simulation of that cosmic web collapsing over time. Okay. I'm not a simulator, though. I'm also an observer, but I attempted, this was my late night venture, to offer a metaphorical simulation of this process as well. Oh gosh. Okay. So the same thing, described a slightly different way. So we have a primordial soup of the entire universe, followed by a Swiss cheese-shaped intergalactic medium, and the holes just get bigger over time. Cheese is more concentrated. We zoom in, and then bold stars form there. That's awesome. Then we have happy galaxies minding their own business. Oh, but galaxy cluster core just swallows it all up. That's not very nice. And these spiral galaxies catch on fire as they fall into the galaxy cluster, and then poof, we have our galaxy cluster at the end. And it's a very hot place, and everyone's moving there at the end, so it's kind of like Austin, Not right now, but you know what I mean. You know what I mean. Okay, so here's a gorgeous picture of a galaxy cluster, Abell 370. It's one of my favorites. I just wanted to put this out to the audience for you to shout out, what kind of characteristics of the cluster do you see in this image? Like, what are some of the striking patterns that you see? Yellow, lots of yellow. Yeah, that's a great one. Gravitational lensing. Yeah, great. Okay, so I'm going to just cut it off there because those are the two that I prepared for. So, okay, so yeah, gravitational lensing. So there are these cool gravitational arcs. They're like little strings around the edge. Do you see them? They're really faint. And they appear to arc around the center of the galaxy cluster. And indeed, those are galaxies in the background. And I'll get back to those in a moment. Super cool, though. And then we have lots of yellow. I prefer to call them burnt orange galaxies. Woo! Yeah, so like tons of burnt orange galaxies. Not a lot of spiral galaxies like the Milky Way living in galaxy clusters. So why is that? So this brings me to the topic of jellyfish galaxies. This is one of my favorite images, and I just had to design the talk so I could show this. Yeah, so spiral galaxies, they do fall into galaxy clusters, and they undergo a morphological transformation. So they're actually changing from a spiral into something that's more like an elliptical galaxy as it falls in. And this is it's a beautiful image of gas being stripped from the inside of the galaxy. It's cold gas as it lives in a spiral, and it's encountering this process which basically just strips the gas out of the galaxy, and you can see this hot trail of X-ray emission, which actually follows behind. So if you didn't get the analogy here, jellyfish galaxies, here we go. That's my little illustration of a spiral falling in. Yeah, that was my late night. Okay. Okay. Oh, this is just a cool movie. So, a part of a blank piece of sky here, and we're zooming in. There's some space music, so I really wanted to play this. You feel like you're falling into doom. So this is zooming in on a galaxy cluster called Abell 1689. And you can see, these aren't like easy things to find with backyard telescopes. They're kind of faint. But once you see them with, Hubble Space Telescope, they're really, really striking. Okay, so here we are, arrived. And then, it's beautiful purple glow. What's up with that purple glow? Okay, so here's the same galaxy cluster. It's flipped. No, sorry. As you would see it from an optical telescope, like the Hubble Space Telescope. But what's really cool about galaxy clusters is you could add X-ray vision to this, and you see it in a whole new light. So there's this diffuse glow that permeates the entire cluster, and that actually traces hot intercluster gas. So this is gas that sits between the galaxies. Remember, all the gas is kind of stripped off of galaxies as they fall in, but also a lot of gas is falling in the cluster that never entered galaxies to begin with. And that gas becomes very hot, and it actually emits radiation at X-ray wavelength. So you need an X-ray telescope to see this. And fun fact, actually most of the matter, the normal matter, not the dark matter, the normal matter in galaxy clusters lives in this hot intercluster medium. It doesn't actually sit in the stars inside the galaxies. So that's super cool. Here's some other X-ray images of galaxy clusters out there. We have the Perseus up on the left. Has anyone seen the one on the lower right and know what that's called? Anyone? Okay, I heard it. Yeah, bullet. The bullet, because it kind of looks like a bullet or something. Yeah, so it's a bullet cluster, and this is just strikingly beautiful. These are actually two galaxy clusters that are in the process of merging. So galaxy clusters are big, but merging galaxy clusters are super big. So the pink stuff is that X-ray emission, the hot intercluster gas, and the blue here is meant to represent the center of mass and where we infer the most of the dark matter lives. And what has happened here is these two galaxy clusters have intersected, passed through one another, and the gas kind of collides in a traffic jam in the middle, but dark matter just kind of passes straight on through. And so these two will eventually coalesce and form a more massive structure. Galaxy clusters are also useful as telescopes. So even if you don't care about galaxy clusters, which you should, you can use them as telescopes to look at even more distant things. So this is a simulation of Hubble Space Telescope looking at a cluster, and there's a galaxy behind it. And we can't do this in real life, but we're going to move that galaxy behind it. So it's going to move behind the cluster, and you see this really cool effect of lensing. And that basically, as if it, there was a warped piece of glass in front of you. So you get higher resolution on looking at the details of that galaxy in the early universe. Here it is again. So you see more detail. You see multiple images of the galaxy. And that can be a remarkable tool for studying the very early universe. So that's why, we chased after the Hubble frontier fields. We can use them to study the distant universe. Okay, my last comment here about galaxy clusters, it's really hard to boil this down to a short talk, but is that they also really need dark matter. So without dark matter, clusters would just fly apart. This is a cool visualization of a movie where, here's a cluster with dark matter, and then because it's a simulation, we can just turn off dark matter at some point right there. And the galaxies, because they're traveling so fast, it's like a swarm of bees. They're traveling so fast, they just like fly away without dark matter. So dark matter really keeps it all held together. So have no fear. Galaxy clusters aren't going anywhere, even though the universe is expanding and accelerating in that expansion. So galaxy clusters, so they're kind of like Austin. They got enough of the weird stuff, the dark matter, to stick around for the long haul. So thank you.
Thank you, Dr. Dustbuster. We have some time for some questions. Here over on the staircase.
Largest gravitationally bound objects in the universe. So, yeah, okay, yes, superclusters are slightly bigger than galaxy clusters. That is correct. So there is like extended structure, and we can have detailed arguments and philosophical discussions about whether or not certain objects are gravitationally bound. There's also a whole range of clusters out there. Like there are supermassive clusters that are kind of like what people call superclusters, and then there are, smaller clusters that are like 10 times smaller and no big deal. So there's a range. That's absolutely correct. Yeah. That's a great question. No. So, galaxy clusters are, I don't really have a good answer for that. So in the present day, that is not true. So there are a number of, it is true that galaxies today will sit in filaments that are connected, by galaxy clusters, but the vast majority of galaxies, and certainly spiral galaxies, don't live in clusters. Yeah.
Any more questions? Oh, there you go, up there on the balcony.
I know for us plebes, you present these beautiful and
right.
lovely.
Yeah, my drawings, right? Yeah. Okay.
But the actual data that you work with, is it mostly the visual spectrum, or are you mostly in other ranges?
That's a great question. So, different tools for different parts of this problem. If we're looking at galaxy clusters in the present day universe, you want more than Roy G. Biv. for example, that X-ray data tells us the temperature of the gas and the density of the gas, and how much mass is in the gas as opposed to in the galaxies. And we also look at radio data, because actually there are features in the X-ray data which we can't explain alone with X-ray or optical, and so then we have to go to radio, and then we see, oh yeah, there's this giant jet that's coming out of a galaxy, and it's puncturing like a hole in the X-ray in the hot intercluster medium. So more and more astronomy is multi-wavelength. If you really want to understand the entire evolution of a given type of object, you want the entire spectrum. And it just becomes hard observationally to gather all that data. Yeah.
Any last questions? Okay, last one right there.
Yeah, so active galaxies are more likely to be outside of clusters. So the fact that galaxy clusters are predominantly made up of elliptical galaxies, there's not a lot of action in elliptical galaxies. But we do think that galaxy clusters in the past, when they were still forming, were extremely active. Like, they were filled with active galaxies, much more so than the field. The field is just like normal space. So there's been an inversion, basically, over the past 10 billion years, where the galaxy clusters used to be very active, and now they're not. And the active galaxies that are out there are in the field. Great question.
Okay, great. Let's thank Dr. Dustbuster again.
Thank you.